Hello student, see here the transfer function of a general system GS can be expressed as a ratio of two polynomials. That means GS is equal to NS by DS and this is equal to Bm s to the power m plus Bm minus 1 s to the power m minus 1. This whole divided by an s to the power n plus an minus 1 s to the power n minus 1 like this. Okay. So see here ns is the numerator polynomial of the transfer function and ds is denominator polynomial of the transfer function. Okay. We have already studied that the roots of the numerator polynomial are known as zeros of the system GS and the roots of the denominator polynomial are known as poles of the system GS. Okay, so here give the definition of poles and zero. So what is poles or what do you mean by poles? So see, the poles of the system GS are defined as the roots of the denominator polynomial. That means the values of s for which ds equal to 0. Okay. Now, what is zeros or how we define 0? Okay. So see, the zeros of the system GS are defined as the roots of the numerator polynomial. That means the values of s for which ns is equal to 0. Okay. Now see, in this equation, that means gs equal to ns by ds and this is equivalent to bm sm plus bm minus 1 s to the power m minus 1 and this whole divided by an s to the power n plus an s to the an minus 1 s to the power n minus 1. So in this equation, the order of the numerator and the denominator polynomial are m and n respectively. That is, the system has m zeros and n poles. The poles and zeros of a system may be real or complex. If they are complex, they occur in conjugate pairs. The poles and zeros can be plotted in the S-plane. Okay. So see, this is our S-plane. Okay. So we know that the variable S is a complex variable and defined by S equal to sigma plus j omega. Okay. So see, we know that the variable S is a complex variable and defined by S equal to sigma plus j omega, where sigma is real part of S and omega is the imaginary part of S. Okay. See this graph. So see, the horizontal axis of the S-plane is known as real axis since omega equal to 0 for all points on this axis. Okay. And therefore, the real axis is S equal to sigma. And the vertical axis of the S-plane is known as imaginary axis since sigma equal to 0 for all points on this axis. And therefore, the imaginary axis is S equal to j omega. Okay. The origin is represented by 0 plus j0. The region to the right of the imaginary axis is known as right half plane and the region of the left of the imaginary axis is known as left half plane. The poles in the S-plane are designated by symbol cross. That means pole represented in S-plane by this symbol, okay, and 0 represented in S-plane by this symbol, okay, clear? So the poles in the S-plane are designated by the symbol cross and the zeros are designated by the symbol 0, okay, clear? So this is our S-plane, okay. And the horizontal axis of S-plane is known as real axis since omega equal to 0 for all points on this axis, and therefore the real axis is S equal to sigma, and the vertical axis of the S-plane is known as imaginary axis since sigma equal to 0 for all points on this axis, and therefore the imaginary axis is S equal to j omega. The origin is represented, that means this is our origin, okay. So the origin is represented by 0 plus j0. The region to the right of the imaginary axis is known as right half plane. Here I have mentioned which side, okay. So the region to the right of the imaginary axis is known as right half plane, and the region to the left of the imaginary axis is known as left half plane. The poles in the S-plane are designated by the symbol cross and the zeros are designated by the symbol 0. Clear? Now I have taken one example, okay. So here I have taken one example. Here the example is find the poles and zeros of the transfer function of this gs equal to s square plus 3s plus 2 divided by s plus 4 and this whole into s square plus 6s plus 25, okay, and sketch the pole 0 plot. So here I have taken this example, okay. So now we see how we identify pole and 0 in S-plane, okay. So see the solution here given gs. So gs, we know gs equal to ns and ds. Ns is numerator polynomial and ds is denominator polynomial of the transfer function, and this is equivalent to this given transfer function s square plus 3s plus 2 and divided by s plus 4 into s square plus 6s plus 25, okay. So see the order of numerator polynomial is 2. Therefore, the number of zeros are 2 and they can be obtained by equating the numerator polynomial ns to 0. Okay. So, see how we find the this see how we find the zeros and poles, okay. So how we find, so see here the order of the numerator polynomial is 2, therefore the number of zeros are 2 and they can obtain by equating the numerator polynomial ns to 0, okay. So our numerator polynomial is this s square plus 3s plus 2 and this is equal to 0 for finding the 0, okay. So if this is 0 then we find there is two value of s, one is -1 and another one is -2, okay. So in this way we get the zeros. So the zeros are, first zeros I have identified by z1 and z1 is equal to -1 and second zero z2 and this is equivalent to -2. Now we will find poles, okay. So see the order of the denominator polynomial is 3. Therefore, the number of poles are 3 and they can be obtained by equating denominator polynomial equal to 0. Okay, so our denominator is s plus 4 into s square plus 6s plus 25. So if we put this equal to 0, then we find the poles. So if we put this equal to 0, then our pole are this. First pole is P1. I have identified first pole P1 and P1 is equal to -4 and we have two complex complex pole. So first pole is P2 equal to minus 3 plus J4, and third pole is P3 equal to minus 3 minus J4. Okay, so now we will see how we sketch this 2 pole and this 3 pole and 2 zeros in S plane. So see here I have identified all the poles and 0 in this S plane. So see our zeros are 2, that's our minus 1 minus 2. So here I have mentioned where is Z1 and Z2. So Z1 and Z2 basically minus 1 and minus 2, that means these are zeros, and these zeros I have mentioned by 0. Okay, and we have 3 poles. So poles are identified by P. So first pole is P1, so P1 is minus 4, and other 2 poles are minus 3 plus J4 and minus 3 minus J4. So here see, this is our second pole, this is our first pole, and this is our third pole. Okay, and this is our 0. Okay, so you understand how we plot pole and 0 in. I hope you understand how we sketch pole and 0 in S plane. Okay, now I will discuss stability in frequency domain. Okay, so see, we have already known a system is said to be bounded input and bounded output stable if for every bounded input the output is bounded. Okay, this criteria is known as Bibo stability criteria, and we know if for a bounded input the output is bounded, then the system is stable, and if for a bounded input the output is unbounded, then the system is said to be unstable. Okay, now let us study the analysis of stability in frequency domain. So let us consider the transfer function of a linear time invariant system. Okay, so here the transfer function is Gs, and this is equal to Ns by ds, and this defined by this equation. Okay, so see here the denominator polynomial of the transfer function equal to 0 is known as characteristics equation of the system, and the roots of characteristics equation are poles. The denominator polynomial of Gs can be factored, and we can express Gs in partial fraction form like this: Gs equal to A1 divided by S minus S1 plus A2 divided by S minus S2 plus dot 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 An divided by S minus Sn, like this. Okay, so see the poles of the transfer function Gs can be either real, imaginary or complex. The poles may lie in left half of S plane or right half of S plane or on j omega axis also. Okay, depending upon the location of poles on the S plane, the system has different type of impulse responses. They are real poles, complex poles, and repeated poles. So see, what is real poles? So see, if a pole is in the left half of S plane, the corresponding partial fraction form is AK divided by S plus A. This is general form. If a pole is in the left half of S plane, the corresponding partial fraction form is AK divided by S plus A. Now, if we taking inverse Laplace transform of this, then we get AK e to the power minus AT ut. Okay. So, see, if the pole is a real number, then Sk equal to minus A. and mod of A is greater than 0 and is located in the left half of S-plane as shown this first figure, that is figure number A. So see, if the pole is a real number, that is sk equal to minus A, and mod of A is greater than 0 and is located in the left half of S plane as shown in figure A, then the corresponding impulse response is like this. The corresponding impulse response is ak e to the power minus at ut, and this is like this. Okay. So see, this indicates that after some time the impulse response dies out to 0. Okay. So if sk is positive, then the pole is in the right half of S plane and the corresponding impulse response is ak e to the power at ut. That means this. So in first case, that is figure number A, pole lie in the left side of S plane. Okay, pole lie in this side. Okay, that's why impulse response is this. But in second case, that is in figure number B, pole lie on the right side of S plane. That's why the impulse response is like this. Okay, that is, the impulse response increases without any bound as t increases as shown in figure B. Okay. Thus a stable system GS must have poles in the left half of the S plane. Okay. So if the pole is at origin, the response is a constant value for t greater than 0. That means in figure C, the poles situated or lie at origin. So for this, the impulse response is constant value. Okay, the response is a constant value for t greater than 0. Okay, so these all are happen if poles are real. Okay. Now come to second case. Second case means if our poles are complex. Okay. So see, if the poles are complex of the form S equal to minus A plus minus JB, okay, then the transfer function GS in partial fraction form is this. Okay. So see, if real part A is negative, then the poles are on the left half of S plane as shown in figure A. Okay. And the corresponding impulse response is of the form A e to the power minus at cos omega t plus phi. Okay. Now second case, if A is positive, then the poles are in the right half of the S plane and the corresponding impulse response is A e to the power at cos omega t plus phi as shown in figure B. Okay. Note that the system with left plane poles have impulse response that is decaying sinusoidally and approaching 0 as t increases, whereas the system with right plane poles have impulse response that is increasing sinusoidally without bound. Okay. If the poles are on j omega axis, then the impulse response is of the form A cos omega t plus phi. In this case, there is no damping and the response continuously oscillates. That means their sustained oscillation occur between two limits as shown in figure C. Okay, so these cases are happen if our poles are complex.